Well, welcome everybody. I hope you've been enjoying the CppOnSea conference in a brand new way, as we're all doing things in a brand new way this year. And thank you to Jim Basnight. He did a great job. Thanks, Jim. You may recognize Jim if you've been to CppCon before. He is the band leader for the CppCon house band. And so he didn't have a band to back him up today, but he did a nice solo gig for us. And so we appreciate that very much. Well, it's already the last part of the conference, and I hope I don't let you down now, but I want to talk for a moment about programming languages more generally. There'll be lots of C++ examples, but even a few languages from outside programming languages, examples from other domains. But we're here enjoying either a morning if you're where I am, or a late afternoon where you are. If you've got your coffee or your water, this was coffee, it is now water. Please enjoy as we go and speak for a few moments about what it takes to introduce something new. And we've all seen new programming languages, we've all seen new products, perhaps even participated in bringing those to the market. And we've also seen a lot succeed and even more fail. So what I want to do for the next hour or so is to answer the question, why will this new thing that you're building, or that maybe somebody else is building and trying to get you to adopt and use or invest in, why will this new thing work when these other things that are kind of like it, that have tried basically the same thing before, haven't done so well or haven't succeeded? And as we go, what we're going to try to do is to use the Q&A feature. If you look at the sidebar in the user interface you should see a Q&A tab. Feel free to put your questions there. And there's also a way to vote on them. So I really like this. I've wished for conferences to do this for a while, so it's great to see the remote platform has this. Please put in your questions and vote up other people's questions that you would particularly like answered. And what I'll try to do, even before the end of the talk, at a couple of places where we stop at major sections, I'll ask Phil to relay some of those, if there are any, and we can take a break and answer a few. And then hopefully we'll have some time at the end as well. So let's get right into this question and see how we get to the shining city on the hill of a new product that is widely adopted and loved. Now, there are a few things I'm not going to talk about that there are many talks about and are largely things that we understand we need to know to do well. We know we need good funding. We know we need a decent team and a good design. We know we need to have successful quality, rollout, marketing, all of these things. And they're necessary but not sufficient, to use a mathematical term. And they're not really the things that we first think of when we differentiate a why would yours next effort succeed when others have failed, because these are easy things to point to that are pretty much table stakes everybody should have. Instead, what we're going to focus on for the next hour is strategy differentiators that affect the design of our product. Strategy differentiators that affect how we designed the product from the very beginning. And three of those things that come up over and over again are value. What is the value proposition? Availability. How available is it for users of the old thing that we're competing with or replacing? And then especially where we're going to spend most of our time and where both of those flow into the question of compatibility. So sections 1 and 2 are actually fairly short. Section 3 is where we're going to spend most of our time, but they all link together with aspects of compatibility. So let me define, first of all, what I mean by what is a new thing. Now, it can be some competing new product, say a competing new programming language that gives you a better way to do something. And we have examples of that in the programming language field, many, many examples. But it can also be the next version of the existing product you already have. Remember, for any established product, vNext's biggest initial competitor is the previous version that's already out in the field. And we have examples of this. For example, C99 competed with C89. C++20 is in the final process of approval, and as compilers ship that over the coming year or so, it's going to be competing with, guess what, C++17 and also 14 for those who have not moved on from 14 yet. And we have many examples of this, but perhaps one of the most striking to me, and so I thought I would share it as just one example, is Visual Basic. Because if you've been around for a while and loved Visual Basic and the way it automated COM in the 1990s, you might have been one of the many who were chagrined when Visual Basic.NET came along with the same name, but it's not the same language. It was totally incompatible. It took many breaking changes. And even though it had the same name, to this day, there are two Wikipedia pages, one for Visual Basic and one for Visual Basic.NET. That in itself is a testament to just because you're the next version of the same brand product does not mean you are going to win adoption. It took many, many years, and even to today, where Visual Basic 6 is still being used. Let me just add a note about how many programming languages there have been. So this information is courtesy of Bjarne Strustrup, who did a survey and a study of this about 20 years ago. In 1969, Jean Sammet published an important book on programming languages, and she listed at the time 120 programming languages. And this was a very selective list that excluded a lot of small languages that were being used as research languages. But even by 1969, near the dawn of computing still, there were 120 different major programming languages that she documented. And circa 2000, Bjarne actually went through and did a study where he estimated about 10,000 languages at that point. And he did it by sampling several years, all available sources for documented languages. Now, he counted things like named dialects, macro assemblers, academic languages, and that's a lot right there because almost every university seems to have their own research language. And there are many thousands of universities. But there's also process control and all sorts of specialized languages. And he came up with it pretty much no matter what year you sampled, it was roughly 200 significant languages a year, not even including the ones that we create for our hobbies. Probably like me, you've created some of those yourself. Now that number is going to be well north of 10,000 that have been created, but we only have a few hundred survivors that have been maintained or used for more than a small group. And we have maybe tens of languages that have been used by lots of people for an extended time. And certainly the list is of million user languages is very, very short. By the way, Bjarne asked me to do one thing, and that is to invite other people who might be interested in this to do what he did back around 2000 and do it again and update this study. So if you're interested in doing that, please send him mail. That's a request. And if you're interested in updating this study. But this already gives us a pretty good idea of a large fraction of languages fail. And most of these were never intended to be used by a million programmers, but a lot hope to be. And very, very few ever achieved that. Let's talk about why. First, by starting to talk about this value, this shining city on the hill, why would I want to go there? Why would I want to go to NewThing in the first place? That's the value proposition. We've all heard about the elevator pitch. You're in an elevator with an executive and you have about 30 seconds to explain to them why they should love your project. How do you articulate that value in that short a time? The easiest way to do that is to tie in to address known pain points with something that is already very familiar. If you can say, we are going to fix problem A, B, and C that executive already knows about, or that new user already knows about with some existing project, then you immediately have a connection to old thing. You're already starting to build the bridge we're going to be talking about later. And you've given them an orientation. You've rooted them in something they already understand, and we have said, we're going to take you from here to there across this gap and solve this problem for you. So when you hear about the elevator pitch and people say, have a condensed version of your pitch, of your value proposition, think the simplest way and pretty much the only way you're going to get that into 30 seconds is to clearly articulate how you are solving a known pain point. And in this case, in programming languages, known pain points that already resonate or already well understood with some existing language. So JavaScript is an easy example to point to because there's the JavaScript book and then there's JavaScript, the good parts. And Yes, we can argue about whether there should be JavaScript, the good parts, but here already on the screen, just in the sizes of the books, is a clear known pain point with the complexity of JavaScript, which is absolutely a useful and foundational language for our modern web. And yet, we don't need all of that in order to have the benefit. And Dart and TypeScript are two well-known languages that have clearly articulated this is the pain point that we aim to solve. Other languages do have similar pain points that can be addressed. Notice the photo credit is to Bjarne Strustrup. Thank you for Bjarne for asking that I include this slide and for providing this picture from your desk at home in quarantine. But let's talk about value just for a second, because if you've ever been involved in a project where people say, we're going to make this new thing because we know this clunky old legacy code base or whatever it is we're replacing, we know all of its problems, and we're going to make something that's so much better. Enthusiasm is great, but one classic mistake is underestimating the value in this legacy, old, crufty thing that also ships and works and is being used. It's proven, it's in the field. It may have flaws, and it's great to want to fix those, but do not ever fall in the trap of dismissing the great value that's there, and especially the cost of re-achieving the parity with that value. Because if you're going to siphon people off to your new thing, even a new version, a reboot of the same product, you're going to be asked for compatibility. You're going to be asked for similar features, for similar performance, for similar stability. And almost always, when I've been involved in such a project that tries to make a major change, we get to 90% of the way there, and then we spend the rest of the time doing the other 90% of the work. So both of these affect adoption because they're about the value of the thing you're about to let go of and you're asking people to let go of, and the value of the new thing in order to be able to adopt that new value. Now here's a counterexample. If you look at Visual C++ 6, which was released in 1998, it was a very popular product. A lot of users used it. In fact, 10 years later, as I was now, by this time, in the meantime, had joined Microsoft and was working in the developer division on the Visual C++ team, one of our big problems was lots of people were still using version 6. It was actually very hard to get people to upgrade from version 6, and they had good reasons to stay on the old version. The new IDE might have sounded snazzy. It had lots of features, but it was slower. It was cumbersome to use. And when you have a regression in usability, that is a form of incompatibility. You are breaking a workflow of somebody who was able to do something in a clear way before and can't now, or just in the same way, but it takes way too long now. For instance, customers kept complaining 10 years later they could still write and debug an MFC program better and faster in the 10-year-old product than in the one we were shipping today. To the point where in 2010, we publicly at PDC and other events said that our slogan for Visual C++ 2010 was 10 is the new 6. The fun story behind that is that that largely succeeded in addressing many of the pain points and getting customers to move on so they could get the new features and new security patches and other things, the other benefits of being on the new version. It turned out that 10 was the new 6 in another way too. People were stuck on that then for the better part of the next decade, a large fraction of customers. So yes, 10 was the new 6 in a couple of ways. But the contributing factors that prevented customers from moving were UX incompatibilities, source incompatibilities, binary incompatibilities. And when both of those happen at the same time, that's the opposite of a virtuous cycle because it keeps people stuck on old thing. One other counterexample I want to throw out is often we see a desire to clean up a programming language by making it super simple, so to the point where simplicity and terseness becomes a top priority. And it's good to be simple and terse, but that should always be a means to an end, not an end in itself. So yes, C++, for example, is complex. JavaScript is super complex. But when we aim to simplify it, it's not the complexity that's the problem we want to solve. It's the toolability and usability. So it's the complexity is causing the problem we want to solve. It may be the root cause, but the goal is to solve the effect, which is not the complexity, but the toolability and usability. It is easy to overdo simplicity when you make that the goal. For instance, I think all of us know how to build a simple language. Alan Turing did it before there were other programming languages, and you define the Turing machine. And then you fall into the Turing tar pit, where you have a very general set of primitives that's the assembler of assembler in terms of being low and general, but it means your programs are not simple anymore because it becomes very difficult to read code. An example, a well-known example is on the right-hand side, which is very Turing-like, but this leads to write-only code and small programs. So don't fall into the pitfall of conflating simplicity as a goal rather than as a means to a goal. So let's take a break there before we leave the value proposition, addressing known pain points. Do we have any questions, Phil?
No questions in the Q&A yet. One's just popped up. I think we just have to wait for the 20-second buffer to flash. So yeah, on the topic of shiny new thing fads, do you think these might show the problem of having an overly belief-centered value system as opposed to one which is rooted in practicality?
I didn't quite catch the second half of the question. Could you say it again?
So do you think these might show the problem of having an overly belief-centered value system as opposed to one which is rooted in practicality?
Yes, the overemphasis on ideology. We all sometimes fall in the trap of making decisions for ideological reasons. And yes, that can lead you down a dead end where you become increasingly disconnected from the reality of users on the ground. So one way to deal with that is by talking to customers, getting out of your shop and actually, especially watching them use your product, and that kind of interaction and listening to what they say, not quickly dismissing it. Even when feedback, even on a personal level, but especially about your product, might be given in an acrimonious, impatient way, they're telling you something you probably need to know. Look past the way it's presented and try to find the feedback on what's missing or what there's just too much of in your project.
That seems to be the only question for now. There was a lot of talk about Lisp, but I think
we'll have another opportunity at the next section. So let's now move from value to talking about number 2, which is availability. How do I make the value available to users of old thing? Again, this affects our design and the strategy we use to create our product. So the Holy Grail is that any old thing project or installation out there can easily start using NewThing. If I'm doing a new tooling mechanism, I should be able to use that in any factory. In any tool and die maker should be able to use that new tool where they are already using the old tool that we're trying to do a better job of. This especially matters to programming languages. An example outside the field of programming languages, but from tech, is a new kind of phone. So the iPhone back in 2007 was a very radically different design of phone. It was very different in other things that had been happening before. So sorry for the extra audio. This is what we get when we do a live show from home. This is pandemic time. And the availability that it's available to all customers of the existing, in this case, phones, has to be a design goal from the start, but we can grow into it. So the example with the iPhone was that it worked on all the existing networks. Any network where you had a phone already, you could use the iPhone. Now, it didn't initially in all markets work on all networks, but there was nothing in the design that prevented it from being used on any networks in the future just by adding another chip. There was nothing that inherent that required building a whole new infrastructure or only working forever on only one kind of existing infrastructure. And today, the iPhone is being used on all networks, all existing networks that existed then, in the whole world and moved along with them as they upgraded. C in the programming languages was by design designed to work on a wide range of hardware. Bjarne Stroustrup famously said of Dennis Ritchie, they said that it couldn't be done, and he, Dennis Ritchie, did it. And the thing they said that couldn't be done was that you could have a language that emphasized performance, but that was portable so that you could get reasonably portable performance from the same source code instead of having the language for each processor, which had been the rule before. Now, you could say that it was for PDP-style hardware. Turns out there was a lot of that, and that has won the field. But this was by design. Dennis Ritchie had to design the language for that performance portability. Now, Bjarne learned from that, and CFront did something similar. It was the first C++ compiler, and it compiled to C, which means it was usable anywhere C is. So just as C was available on every major processor, C++ was available anywhere any C compiler was. And that really reduced the barriers to being able to adopt the new thing. It included leveraging, not having to reinvent the C optimizer and the system linker for performance and compatibility. Python, similarly, its reference compiler was written in C. So again, it could be used wherever C was. This was a design choice up front, whereas if they had made other design choices, like say, writing it in Java had that been available at the time, that might have started to reduce the platforms where it was available, or at least the requirements of what you needed to install in order to be able to get up and running. TypeScript, similarly, is in the same bucket of languages where every TypeScript program compiles to JavaScript, runs on any JS runtime. So it's available wherever JavaScript already was. Now, so far we've been talking about runtime and compile time, but let's talk about Swift and Roslyn now in terms of tool support. So Swift, when it came out and was released as a successor to Objective-C, and we began that transition, it was available to every Xcode developer on every platform that Objective-C supported at the time. Now, since then, it's gone to even more platforms that Objective-C wasn't supported on before. But right out of the gate, if you could run Objective-C, you could run Swift because it was available through Xcode on all those same platforms. Roslyn, for those who weren't familiar with that in .NET land, was a new C# compiler where, no small feat, let's just replace the entire compiler, which has a very high bar for compatibility. It was available to every Visual Studio developer on every platform C# supported, Visual C# supported. All of these affect the availability. You want to have the new thing out where old thing people can at least try it and start using it. Now, it doesn't have to stay with that breadth play. So those examples like JavaScript and TypeScript started with a breadth play. So the availability breadth play is I can use it wherever the old thing exists already. But that doesn't mean that I can't also write custom additional support for particular platforms. So for instance, CFront, because it compiled to C, it was available anywhere C was. But then when Zortex C++ came along, it was the first native C++ compiler. It targeted what was turning into a very popular operating system called DOS, and also was compatible with the Windows SDK. And that greatly increased the reach, not because CFront couldn't already be used on some of those platforms. It was available anywhere C was, but by having a custom implementation for major platforms, that further accelerated the adoption of C++ and made the availability even easier on important platforms. So any questions on the availability part before we continue?
So we actually have one question from Cybrand. He wants to know, what's your dog's name?
The dog's name is Stevie. And he's a rescue. He's still getting used to being in a forever home. He's only been here a few weeks, and after spending about 6 months in shelters and fosters. So he's getting there, but he's a little upset this morning.
Thanks. Yeah, that was the only question. You're getting a lot of comments in the chat though, so everyone's with you.
All right, let's continue then with the third, which is compatibility. And we've already talked about compatibility a few times, because when we talk about the shining city on the hill, the value prop, that's where we want to go. We talk about availability to make it accessible to as large an audience as possible, but then we have to get them there. We have to actually help them get across whatever chasm that we're solving and be able to adopt the new thing. So when you talk about an adoption function, it's measuring effort versus value. I expend this much effort horizontally and I get this much value vertically. Well, which adoption function would you prefer? One where I have to put forth a lot of effort on the left-hand side before I start seeing any value? Or one where I can put forth just a little effort and already be seeing value? Well, one's a step function and one's a ramp. And step functions aren't necessarily bad. Stairs are steps, but the steps have to be small. If the steps are too big, they become walls. So we want to aim for number 2. To get there, to avoid that adoption wall, we have to have, by design, high fidelity interop with the old thing. And this isn't something that you can easily tack on later. I'll give some counterexamples. The very minimum bar is that any code, in this case of a programming language written in the new language, should be able to seamlessly use the old thing, the old language. You'd ideally like that to go in both directions, but the minimum bar is that new code be able to seamlessly invoke old code, because that means I can start using new thing in an existing project and start using that project, writing a new code bubble. So there's 2 levels here, and you can probably relate to these in adopting a new programming language or tool. If I'm using an old thing project, I'm writing in a C project, for example, I should be able to write new things, say a C++ file, side by side and start seeing benefit. So even if most of my project is still .c files, I should be able to start writing a .cpp file in the same project, which means understanding the same build system, the same link in interop, and start seeing benefit. To do that, I had better be able to seamlessly invoke old thing from new thing, invoke C from C++, and be able to be used in projects that use C. But the Holy Grail is actually even higher. The Holy Grail, if we can achieve it, is that an old thing project can start using new thing in just one place, ideally writing just 1 or 2 lines of code, and start to see some benefit. Now, small use means small benefit, but as soon as you can start seeing benefit, that's the trigger that we're aiming for. We actually achieved that in C++ and in TypeScript. So in C++, you can largely rename a .c file to a .cpp file, at least you could in the 80s, and you mostly can now, add one class and start seeing benefit. That's a high level of compatibility, not just link, but source compatibility. TypeScript, and one of the reasons for its major success is it did the same thing. You can rename a .js file to .ts, add one class, because TypeScript added static typing, and start seeing benefit. And then you're in this beautiful sweet spot where I can take an old thing project, once I've got the value prop and the availability so that I want it and I can get it, when I start using it, I can immediately start seeing value. That is the ramp we're looking for. And ramps are not just for old people. We use them all the time to get real work done. Let me give an example from the field of aviation. So maybe like me, some of you are a bit aviation buffs, especially at the beginning of the aviation age and the major advances that were made in the first few decades. If you look at the Lockheed L-1649 Starliner, it was a beautiful, beautiful machine. Entered service, it started production in 1956. It was in service 56 to 58 was when it was in production. The value, compared to other turboprop planes at the time, it was luxurious. It was reliable. In fact, it was the very first plane, the commercially available plane, that was able to make a transatlantic crossing in the westbound direction reliably. Reliably is kind of important if you're an air traveler. It had 10% greater range than its most recent biggest competitor. And it was compatible with existing infrastructure. So the compatibility was there. It did not need new airports. It did not need new terminals. It was able to use the existing infrastructure. And so it had a compelling value proposition. It had a compelling availability. Those were the first two things we talked about. But then it was only in production for 2 years, whereas the Boeing 707 stayed in service until 2013. That's a big difference. And it was, we were talking about the value proposition as well as the compatibility with existing infrastructure, that you could use the Boeing 707 at pretty much all existing airports, airfields, and with terminals that existed. So where we look at programming languages, we see a parallel where, as we mentioned, C++ has a great compatibility story with C. Every C program is a C++ program. That's still mostly true. And any C++ code can call C and a C optimizer and linker. TypeScript has at least as strong a story. It's not just mostly true, it's pretty much universally true that every JavaScript program is a TypeScript program, and TypeScript can seamlessly call JavaScript code. That makes it very easy to get the adoption and avoid the step function. Now, at a non-language level, this applies also to the tooling level, but it highlights how it's required to be done by design. Swift and Roslyn also both had high compatibility. Now, in the case of Swift, for those who may be less familiar with it, Swift has a very strong bidirectional compatibility story with Objective-C, where Swift can call Objective-C and Objective-C can call Swift. There's automatic bridging, header generation, and even tool support, so you can easily see Objective-C code as if it had been written in Swift. Clearly, that tool support had to be done by design. But even the fact that you could communicate between the two languages at all, and that seamlessly, was by design, in this case, on both languages, because Apple owned the major implementation of Objective-C that Swift was competing with. Two major things, where Swift would have been a much simpler project to be able to design a new language that's better than Objective-C if it didn't have to be able to use the same object layout as Objective-C, or have the same reference counted lifetime as Objective-C. If we could improve the object layout while we were at it, maybe make vtables better, and we could use garbage collection or do something that was quite different from Objective-C, you would have a new Objective-C competing language, but you wouldn't have compatibility and adoptability. Instead, Swift uses the same object model, binary layout as Objective-C, and the same lifetime model for reference counting. In fact, Apple began, even before announcing Swift publicly, to build that adoption ramp in Objective-C itself. So when you looked at Objective-C when it got modules and automatic reference counting, those were inspired by and co-developed with Swift, so that when Swift became public, it could continue that adoption ramp that had already been begun, to make it easy to combine Objective-C and Swift, to use both in the same project, and to call bidirectionally from one to the other, because the object model and the reference counted lifetime were the same. Now, when Microsoft built the Roslyn compiler, the next generation C# compiler, it had the same compatibility by design. It adhered rigorously to compatibility tests from the very beginning to make sure that it was fully interoperable, in some cases bug compatible, with the C# compiler. And if it had not done that, it would have been a curiosity as a new C# compiler, but that mostly worked, but that had incompatibilities here and there where, well, maybe we'll try again next year to adopt it. And it wouldn't have had the same compatibility story. For all of these, compatibility was a great cost, but it was also something that needed to exist in order to make it be adoptable. This is often forgotten until it's too late. For example, for JavaScript interop, Dart is still trying to build JavaScript interop backwards into the language. Dart had other problems that needed improvement, but TypeScript made compatibility with JavaScript a high priority from the beginning. Dart had some compatibility, but even now is still continuing to try to improve it. So it's sometimes hard to back into later. Borland's Delphi product is a similar story. It was a great RAD environment that I know many people who loved greatly. It was better than Visual Basic in many ways. And it ran everywhere Visual Basic did on Windows. And it nailed compatibility in that you could build Windows applications seamlessly. But because Borland was a separate company, and unlike Visual Basic, didn't have a close connection with the Windows team, it couldn't control the compatibility, and that became a burden. Maintaining the VCL, the Visual Components Library, in parallel with all of what Visual Basic was doing was problematic. It cost a lot to do, and they were always lagging behind the latest platform features. So that's an example of where even when you try for the compatibility, you need to both aim for it and be able to have sufficient control to be able to determine your destiny and to be able to keep it. A well-known example is Python 2 and 3. This, as we mentioned, was a source-breaking change where you can't compile 2 as 3 because 3 over 2 has a different type and a different value. So that means that even with manual migration tools, as late as 2017, 9 years after Python was released, a study showed that most Python code was still written in the intersection of 2 and 3. In other words, was not using the new Python features that were the whole point of 3 to their full advantage, but only using the intersection with 2. And even though 2.x was frozen and unsupported earlier this year, as late as about 6 months ago, only 90% of Python scripts and users had adopted 3. Now that's still most of the way there, that's victory. But to have even 10% be on an unsupported tool that's not even getting security features shows the heavy cost of incompatibility and the value of compatibility where the old thing still works when people are relying on it. So in comparison to the previous major versions, Python 1 to 2 were 8 years apart. 2 and 3 were 8 years apart. Python 3 has been in the market for 12 years now. I don't know of a Python 4 on the horizon, and it has just now achieved 90% penetration within the past year. So when we look at these examples, we're starting to see a pattern. We see the same pattern with C99. C99 was the second release of the C standard, and some of the additions were controversial and were resisted. In fact, to this day, we mentioned CPython as the Python compiler that gives you reach and availability across platforms. To this day, it only allows selected C99 features because of lack of portable compiler support. It's still largely C89 code. Now, when the third C standard came out, it actually made those problematic features conditionally supported. It added this new idea of, well, you don't have to implement actually all the features in our standard, and it retroactively applied them to complex and VLAs. And this is why you might see some companies producing C11 compatible compilers before C99 compatible compilers, because it's actually often easier to implement C11 than C99, because you can, for the optional features, you can just define the macro that says not supported. So after 10 years, C had to back out of this. And C++ largely has avoided this. C++ has always had 2 value props that are important. The key value prop of efficiency and machine nearness, but also the value prop, because it really is that as well, of compatibility, that any existing C or C++ code largely compiles with newer versions of C++. That stability is a feature, as Bjarne likes to say. So C++ has never been only about the value prop, which was point 1 of this talk. It's also been about compatibility, which is point 3 of this talk. Except when we didn't. So notoriously or famously, in C++ 11, we banned reference counting for a fairly popular type called stood string. This was an ABI breaking change. And it wasn't until 2015, which was 7 years after that change was first voted in committee in the draft standard in 2008, that GCC, one of the world's most important C++ compilers, first shipped a conforming stood string. But even then, it had to then be adopted on every platform GCC ran on. And on Red Hat Enterprise Linux, a major distribution, first turned the conforming string on in 2019, 11 years after the C++ committee decided to take the breaking change. And if you see a pattern here, this is what a decade looks like. This is a decade's worth of calendars with one column for each year. C99 took about 12 years to adopt after it walked back a couple of features to make them optional. C++11 string took about 11 years to adopt on major platforms. Python 3 took 12 years to get to a place where it had achieved 90% adoption compared to its predecessor. And there are other examples. You remember in the Visual C++ team I mentioned that we shipped a version where 10 was the new 6 because we were still competing with the compiler that was 12 years old at that point. If you don't build a strong backward compatibility bridge to seamlessly let people use new thing with old things so they can adopt it, you may still succeed. I'm not saying you won't succeed. All of these eventually succeeded, but you can expect to slow your adoption down by 10 years or more. That's what it's going to cost you. And again, absent other forces, and that's assuming that we're doing everything else correctly. One way to look at this is somebody once said, I don't know who, every time you take a sharp turn, some people fall off the truck. And if you take the turn sharp enough, sometimes the truck falls over. Now, let me talk about two very specific compatibility pitfalls that impede adoption. One is heavy annotation, and heavy can just mean if I need to change one line of code out of 1,000 in my project, that'll make a lot of customers go away. It means I have to start doing a lot of effort before I start seeing value. And this includes viral annotations, and these go in two directions. So downward virality, let's say new functions can only call other new functions, like a red function can only call other red functions. Safe functions are an example of that in some programming languages. A safe can only call other safe functions. Well, that's fine, but it means if I go to an existing code base, I now, to make my function safe, have to annotate all the things it calls as safe. And to annotate them as safe, I need to annotate everything they call as safe. And I end up having to do annotation bottom up. And if that annotation is incompatible, I could actually be canonizing an incompatible dialect as well along the way. But it goes in the other direction too, where I may need to annotate my caller in order to be called. So for example, if a red function, a new function, can only call other red aware or new aware functions, then I have to annotate the caller before I can call this function. And an example in this direction is Java checked exceptions, where if this function throws A or B, I need to annotate every caller to also be able to throw, among other things, A or B and its callers and so forth. And of course, in the case of Java, you have an opt-out where many people just voted with their feet and disabled the feature by saying, we throw the base class of every exception. So we throw everything. And now if a lower level function adds an annotation, throws F, I don't need to go and annotate throws F all the way up to call it anymore and destabilize my code and take this big change. I just said throws exception, which effectively turns off the feature. Yeah, you can throw an F too, fine. I don't need to change the callers, the call sites. People voted with their feet, and we've seen this play out in other kinds of annotation features. So the key thing is we don't want heavy annotation, but especially be aware of viral annotations, and that can go in either direction, down or up. We've seen this in the safe C dialects. This has been a popular indoor sport, is to create safe C dialects for quite some time. And here are two examples, both of which suffered from virality. And in fact, in the second release, 3 years after the initial release of C cured, one of the major things that the type-safe retrofitting of legacy code paper from 2005 tried to do was to infer all the annotations, because the heavy annotations were a great compatibility hindrance to adopting C cured. Now, people continue this indoor sport of creating safe C dialects, and a more recent one was David Tarditi and his team working on checked C. Now, I want to highlight from the very beginning of their project description, if you find it on the internet, It is distinguished by its focus on backward compatibility, incremental conversion, etc. Those are the first two things that this project description hits. What are they doing? They are doing the theme of this talk. They are answering the question, why should your safe Sea dialect succeed when all these others that look pretty similar have failed? What makes yours different? Because Cyclone and Secured, yeah, they both had different kinds of annotations and different kinds of ways of saying fat pointers, but they all did roughly the same thing. So David Tardidi's answer in his elevator pitch is the value prop is we're solving the safety problem for C code. So there's the value prop number one. Availability, we're going to be running on all the places where C is available. That's number two. But compatibility is what makes us different from Cyclone and Secured and all the others, is because we can interoperate much more seamlessly, is the design goal, with C code without a heavy annotation requirement. Now, Tardidi is able to say very clearly what makes yours different when you otherwise look kind of the same as previous efforts. That is a fundamental difference, but it requires design up front to focus on compatibility. The last pitfall I'll mention is false friends. So we've seen this before where the same code means something different. So 3/2 means something different. It has a different type and a value in Python 2 and 3. And that means you either don't allow them in the same source code, which is poor choice number 2. So you can still get side-by-side usage. That's it's okay. But you have to know kind of which one you're in if you're in a Python 2 or 3 file, for example. Or you allow them both in the same source file, which lets you get closer to the change one line of code, write one line of code in NewThing and start seeing benefit. But now in the same source file, in order to know what 3/2 means, I have to look around to see what mode am I in. I probably have a pragma new syntax mode or a version 2 or version 3 mode. And now I can't just read a line of code in isolation and know what it means. So it hurts toolability as well, readability, but also toolability, because refactoring tools now need to know, I can't just move 3/2 from here to here. I have to say, am I moving into another region of code? So then what have we learned about the question, why will yours succeed when all these others that look pretty similar to it have failed? Well, the first is clear value proposition to address known pain. And if you really are addressing a known pain point, this needs little explanation. Availability, so that any user of old thing has a way to easily get your new thing, to be able to try it and use it. And finally, when they have it, they want it, they've got it, to have the compatibility bridge to get them across the chasm. And this requires designing up front for seamless interop with old thing. It's hard to back into later. And if you don't have it, you're probably going to spend 10 years longer than you would. It doesn't mean you'll fail, but it means it will take roughly 10 years longer, because that's what it always takes. At the minimum bar we want, which is good, is I can use new things side by side in any old thing project. The Holy Grail is to use them together, even in the same file for a programming language. I can write one line of code in the new thing and see benefit, like C++ did for C and TypeScript did for JavaScript. So when people talk about sometimes, well, what about a successor to C++? Wouldn't it be nice to clean up this language? Now, there have been quite a few efforts in this direction. What would make a wildly successful one different? Well, probably not the first two things we talked about, because the value is pretty well known. Pretty much every effort in this direction knows they're solving C++'s pain of safety and usability, toolability. So the complexity and the safety and how they manifest in usability and toolability. So most already have that value proposition, so that's good. Availability, wherever C++ is, well, most of them do that because they're available, say, through LLVM, the modern ones, and that gives you reach across platforms. But the one thing that only one language has done, the only language to ever successfully displace C++ in the marketplace, is compatibility. And the only language, if you're wondering, that has successfully displaced C++ from the marketplace is C++ Next. C++17 is the only language that has ever broadly displaced C++14, and so forth. And we hope C++20 will as well. But the reason is because of the seamless backward compatibility bridge with C++. And this is legit hard for C++. It would be very hard for D or Rust or other languages to say, hey, look, you get the ability to seamlessly pound include a header and call anything, any C++ type. That's really hard. Or maybe with modules to import a module. There's high cost, but also high value. Nobody has tried it yet other than the next version of C++ itself. Not having this doesn't mean that a new product or a new language will fail. It just means that everything else being equal, it will take them a decade longer to get adoption than they would otherwise. The good goal is to use it side by side in any C++ project, and the Holy Grail is to write one line of code inside existing old code and start to see benefit. But at the minimum, even using side by side in a project, that includes the ability to seamlessly, at least from new code to old code, be able to have impedance-free calling, full compatibility to just seamlessly use existing code. So to get to that shining city on the hill, how do we answer why will yours succeed when all these others that look like it have failed? Have a compelling value proposition based on solving known pain points. Have availability so the people who now want it can get it anywhere they're using old thing. And third, have compatibility so they can use it right in their old thing environment, at least side by side. But the Holy Grail is to write one new line of code for a programming language or to make first use of a new tool and start to see benefit right away and avoid that adoption step function. So thank you. Sorry that it took 2 tries to finish the talk. But for those of you who are still here, thanks for sticking with it. And if we still have any time for questions, Phil, just let me know. And thanks again for staying long.
Thank you, Herb, for coming back. That was a great recovery there. We do have one question. Well, we have a few questions. I think some of them are for me. But we have one question from right early in that segment. So I'm not sure now if you covered it later, but from Victor, who says, do you think ABI compatibility will forever hold back significant improvements in C++ implementations?
So that's a very good question. So will ABI will forever hold things back? Not necessarily. So when I was describing this, it was specifically also with that very current question and others in mind. Incidentally, when I first gave a short version of this talk at a Dev Around the Sun event a couple of months ago, I happened to see on Reddit that somebody who might even be a C++ committee member said, oh, this was a rant against making an ABI change. And actually, no, it's not at all. It's just pointing out that C++ has never been only about efficiency. It's always been also about compatibility, and those two things go together. We wouldn't be here having this discussion if C++ didn't have a strong backward compatibility, source and binary compatibility with C. But that affects our compatibility going forward as well. The short answer to the question about ABI is there is more than one way to have compatibility. So for example, you can divvy compatibility up into source and binary compatibility. C++ so far has always had both. A very strong backward source and backward binary compatibility story. You need at least the binary one, just like Swift and Objective-C have had to have, and TypeScript and JavaScript, although that's more at the source level as well, but the ability to seamlessly call existing things. But if you're going to make progress on even taking a binary change, you can still have that and still be C++ with an emphasis on machine nearness and efficiency by making backward binary source compatibility always available, but optional. Now, we've never tried that before, but if anybody ever figures out a way to provide full backward binary compatibility, just like we've always had with C++, but make it optional so you only pay for it when you use it, then that would be a fundamental design advance that would unlock a greater simplification and allow us to do things that we couldn't do in a strictly backward compatible world. So there is interesting work going on in those directions. We'll see if any of it bears fruit, but that would be the way to do it, is to make backward compatibility an optional feature. Not optional as in it's not important, it is vital. But so you pay for it only when you use it. And if we can figure out how to crack that nut, then we'll make large progress. And that answer would apply to any programming language, not just C++.
Thank you. And there was another question that came in while you were talking from James Quigley. Is there anything else you'd like to see on the same level as the C++ 11 string change?
And is there any large change I'd like to see there? Well, there's probably a few. The one that Google has mentioned a few times is that there have been advancements in hash functions and hashing. And so those can require changes to the implementation and sometimes to the interface, where adopting those would require taking a breaking change in the implementation. So those can be useful. Just speaking a bit further to the previous answer and tying it in here, this is why I think that any progress in this direction will also be addressing the issue of versioning. And that is specifically for the library, since now we're talking about library types, is how do we version the standard library so that we can have backward compatibility when we need it, but only pay for it when we use it, and still have the option of using the compatible thing or the performance improved thing, or the improved thing, in this case, performance for hashing.
Thank you. And there were a couple of people that wanted to know if they could see Stevie.
Well, Stevie might be shy, but now we're being looked at here. Here, let's see if I can show Stevie. There's Stevie.
There we go. We have it all in this talk.
Yeah, sorry, that's been the most vocal he's been. So thanks for your patience.
There is one more question that's come in. This is a big one, could open up a whole second talk. Do you think a model like C++ Epochs will ever happen?
I don't know. I don't think it's viable in its current form. It's certainly not something you'd want to take regular changes to, because if you look, for example, at the earlier slides, let's see if I can get back to what slide was I just thinking of? Here. Yes, false friends. And so one of the pieces of feedback I've given to Vittorio, who's proposing Epochs, is there are fundamental limitations to what you can do in a model like Epochs, because Epochs is basically doing what I'm calling, poor choice number one here on this slide 42. Turns out the answer to most things is 42. There you go. The idea of saying, I'm in Epoch 1, I'm in Epoch 2, but if you allow now the same source code to mean different things, now you're left with this Hobson's choice. To pick the first horse in the barn or none at all, and poor choice number one or number two. But if you don't allow changes like that, and you don't have another strategy, now you're greatly limited in the kinds of changes you can do. So I think something like Epochs may well be a good answer, but I think there are several improvements that have to be made. First, you can't be making regular changes. That only works when you have a very small user base and you don't mind breaking them, like D1 to D2, for example. Rust is doing it now, but it remains to be seen whether they're doing it because they still have a very small user base in the tens of thousands, which is about 1% of C++'s user base. The other thing is you want to have a general way of being able to make backward compatibility optional, so that you're moving forward, but in a compatible way, and balancing those two things and avoiding pitfalls like this one, false friends, which one of the reasons I put this slide here was specifically with the Python 2.3 transition and Epochs in mind, is that you have to be able to know about this problem and have a plan for how you're going to avoid it in your design, and have a very good rationale for how you're going to address it, or if you're not going to address it, how you're going to avoid it and why that's an okay choice to make that isn't restricting you from the kinds of improvements you can make.
Thank you. I think that's about as much as we can answer.
Right. And thank you again for taking the extra time. Sorry about that.
Well, thank you for coming back. Thank you for a fantastic keynote and for sticking with us. I just wanted to put one more slide up before we finish up. I just thought this was amusing and an opportunity for Timur to take it even further. And also just to answer a couple of the questions, somebody was asking, can we keep the Discord going? That is going to continue running, but it's not really the best place for ongoing discussion after the event. I recommend either the hash include C++ Discord or the CPP Lang Slack for that. And thanks for all the congratulations, which some of which definitely applies to you, Herb. So thank you again for all of that. So that just remains for me to say thank everyone again. Thank you, Herb. Thank you to all of our speakers. And the Remo rooms will stay open till about 10 p.m. UK time tonight. So feel free to stay as long as you want to carry on chatting. And we'll see you again in some form next year. Thank you all. Bye.